Okay, so we've got light passing through a diffraction grating. We've got 0th order here. And then at different angles, you'll get the different orders, the first order and second order. We're going to look at how this equation is derived. Okay, so how is the 0th order formed? So we've got light incident on a diffraction grating here. We've just seen a tiny section of the diffraction grating here. And there's a screen far away. The light will just go straight through. And because this screen is so far away, it's basically parallel rays. And they'll meet with 0 path difference to form the first 0th order maximum. The first order maximum is formed when light goes through the slits and meets at some angle theta on the screen, an angle theta from the 0th order, such that the path difference between the light from the adjacent slits is a whole wavelength. And we can find that path difference by marking a line like this, where here that's the angle theta as well. Okay, so these are 90 degrees, and these sections of the waves, the rays are the same length, except for this extra part. Okay, so this extra path is the path difference. So if we zoom into that, we can figure out what that is. So D here is the distance between the slits. Okay, so slit separation here, and that's the opposite. That's the hypotenuse of the triangle. And to get this path difference here, which is the opposite, we'll have to use sine. So we'll do D times sine theta, and for the first order maximum, that's going to be a whole wavelength. Okay, for the second order maximum, the light's going through it, but now at a larger angle, such that the path difference between adjacent slits is now 2 lambda. So here's the path difference there between the adjacent slits. Each one's got 2 lambda extra. So if we zoom in again, and we do d sine theta, now that's 2 lambda. Okay, so to derive the equation for the nth order, we can just use d sine theta, which is the path difference between adjacent slits, is equal to n lambda, a whole integer multiple of the wavelength for the nth order. Okay, in this question, diffraction grating has a line 300 lines per millimeter. Light with a wavelength of 590 nanometers incident on the diffraction grating. Calculate the maximum number of orders that can be seen on the screen, which is curved here. So firstly, let's figure out the distance between the slits by doing 1 over 300. That gives us the distance between slits in millimeters, and times that by 10 to the minus 3 to turn into meters. Secondly, we write down the equation here, and we want to find the order, the maximum number order. We've got wavelength already, okay, so that's 590 nanometers, so I'm going to turn that into meters, and the distance between the slits we just calculated. So what angle do we use for the maximum order? So the biggest angle you can possibly get in this case is going to be 90 degrees. So I'm going to put sine 90. Sine 90 is 1, so it just becomes n lambda equals d. Okay, so divide both sides by lambda, then you get the maximum possible order. So if I put those numbers in, making sure I'm in meters, I get maximum number of orders is 5.6. So what does this mean? So first we're going to have the 0th order here, okay, and then we can have all the way up to here. It's going to be 5.6, but we won't be able to see that because that's not an actual order. So the 6th order will be off the screen, so that doesn't count. So we have to round down. Okay, so we round down to 5. Okay, but because there's the orders on both sides, we're going to have to multiply that by 2 because there's 5 orders on each side, and we have to add on the extra number for the 0th order. So the total maximum number of orders you can see on the screen is 11. Okay, light composed of 2 wavelengths is incident on a diffraction grating, wavelength of 400 nanometers, which is violet, and 500 nanometers, which is green. Describe and explain what is seen on the screen. So firstly, when for the 0th order, there's going to be an overlap between those two both. So it's going to be an overlap of green and purple, and it's going to look like dark green maybe. Okay, so this is because there's no path difference. But however, for the different orders, the different wavelengths will diffract by different amounts. So as you can see, violet diffracts less than green because it has a shorter wavelength. So how do we know this? So we just take a particular order. Let's say we take the first order. Okay, so we just take the first order, and we know that violet has a shorter wavelength. Okay, and with D is fixed because we're using the same diffraction grating, so the distance between the slits is the same. So sine theta will be smaller for the violet light, and therefore we'll have a smaller theta as well. Okay, so it'll be closer to the center. Okay, so you'll see more violet orders in this case because they're closer together. Okay, but then the 5th order of the violet will actually overlap with the 4th of the green, like this at this point here. So how can we find that? How can you tell? Well, you have to find the lowest common multiple for the path difference. So you can see the path difference for the 5th violet order and the 4th green order is the same. So they'll actually form at the same angle as well. Okay, white light is incident diffraction grating. Describe and explain what is seen on the screen. So firstly, white light is composed of all the different wavelengths of the visible spectrum. So in the middle, the zeroth order will actually just be narrow and white. This is because the path difference for this point is 0. So all the different wavelengths will meet in phase and they'll superpose constructively. And then for the other orders, however, it's going to be different. It's going to be, you're going to see a visible spectrum like this. Okay, and you can see violet is in the inner part here. Okay, that's because it's got a short wavelength, and red is in the outer. That's because it's got a longer wavelength. How do we explain this? Well, you can use this equation here. So for a particular order, let's say the first order, if it's got a shorter wavelength, D is fixed there, so it's going to have a long, smaller angle, so therefore it's going to be the inner part. Okay, and as you can see, they're getting wider, and they're also getting dimmer as well as we move to a higher order, and eventually they might start overlapping.